Now let's go with the second quantization. Why do we need this second quantization? And let's see where we will end with this video. And to start with, uh, in first quantization, what we do is we treat particles individually, and and it certainly becomes cumbersome for systems with many particles. And instead, in second quantization, in the framework of second quantization, in which the fields are basically the states. They are states themselves and are quantized rather than the particles. Now, this approach is particularly useful for describing these many body systems, such as boson gas. Let's say it like that. And now, talking about the Bose statistics, and in Bose statistics, the states are described by occupation occupation number representation. Now, instead of tracking each individual particle, what we do here is that we count how many particles occupy each available quantum state. So here the quantum state plays a crucial role, and the number of particles this quantum state can have. Now for bosons, the occupation number can be any non-negative integer, since multiple bosons can occupy the same state. And let's generalize it, and then let's denote the quantum state of the system. So if I denote this quantum state of this system, say I'll label it as phi of I. Now this is a quantum state, and this I, it runs over all possible quantum states. So I runs over all possible quantum states. So we have a state phi of I, which occupies which which is composed of this I, and this I runs over all possible quantum states. Now, if this system contains bosons, the state of the system is described how many particles occupy this quantum state. So if we have quantum states, and if I label these quantum states for this quantum state, if I label them as, say, phi 1 and then phi 2 and so on so forth, a typical state of the system is described by the set of occupation numbers. So this is an important point. Occupation numbers. And this set of occupation numbers can be labeled as N1, N2, N3, and so on and so forth, where this Ni is the number of particles, in state phi I, which I started with. Now, this is about building a quantum state and the concept of occupation number. Now, what plays key role in second quantization is the creation and sorry, and annihilation operators. Now, what happens in second quantization? What we do is we sorry, we introduce creation and annihilation operators that respectively creates a particle, creates, or I should say, uh, creates a boson or annihilates a particle. So we have creation and annihilation operators that respectively create or annihilate a particle in a given quantum state. Now, for bosons, these operators they obey uh, commutation relations. Now, if I say that, uh, if I assume, let me assume that a dagger be a creation operator, that adds one boson to it adds okay it adds one boson to the state that I have defined, to the state phi I. And let let's call it AI, and let me have AI alone, and let this be an annihilation operator. Annihilation operator. And what it does, it basically removes one boson from the state that I have defined is phi of I. Now these operators, they satisfy the commutation relations. Now what are those commutation relations? The commutation between AI and AJ dagger is chronicle delta IJ. And if we have AI and AJ, the commutation between AI and AJ, this gives us 0, and the commutation between AI dagger and AJ dagger also gives us 0. So these are the commutation relations between these operators. All right. Now, this certainly reflects the fact that bosons are indistinguishable. You cannot distinguish them, and can occupy the same quantum state. Now, the state of the system is described by the occupation number. All right, and we have a general state in the second quantization formalism, and that general state in the second quantization, we can write it like n1, n2, n3, and so on and so forth. Okay. Now, for example, this is my this is a general state in second quantization, and for example, if there are two particles in the state, two particles, if we have two particles in state phi 1 and one particle, let's assume one particle in state phi 2, and no particle no particle no particle in other states, we have two particles in phi 1, we have one particle in phi 2, and we have no particle in the rest of the states. This state can be written. How will I write this state here? So in accordance with this general representation, I will write 2. Okay, in the first we have 2, then I have 1, then I have none, so on and so forth. So this is my uh, this is my general state for what I defined those occupancies. That the first state has two bosons, the second has one. The rest of all states have have no particles at all. Now, the creation and annihilation operators act on these states. The state I have tried to define here, these annihilation operators, they act. So if I start with annihilation operator, okay, so I have a state, say AI cap, okay, and one, so on and so forth to Ni. Now, this AI is the annihilation operator. So what does it do? Basically, it removes a particle from the ith state. So I will have a state out of it as under root of Ni. Then I will have N1 dash 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 to Ni minus 1 dash 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 ket. So this under root of Ni, it's a result of that normalization. So what this annihilation operator does here, it removes the particle from this quantum state. Now for creation operator, okay, so I have AI dagger now acting on the general state n1 dash dash to ni dash dash. So what we get over here is under root of ni plus 1, then n1 dash 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 ni plus 1 dash dash dash. So here what we are doing is we are adding the particle to the ith state by executing the creation operator on this quantum state. Now, proceeding from here, talking about the Hamiltonian in second quantization. I mean, the Hamiltonian of the system, so I should get it out. So, Hamiltonian. Hamiltonian in second quantization. Now, this Hamiltonian of a system, okay, in second quantization, it can be written in terms of creation and annihilation operators. Now, what does that mean? Suppose we have a single particle energy of state phi I. Suppose I have a single particle and I have a state phi I, and this state belongs to this state is EI, epsilon I. Then the Hamiltonian for the non-interacting, suppose there's no interaction between these photons, the non-interacting Bose gas can be written as H cap is sigma I, okay, EI, and AI dagger AI. This is my Hamiltonian for a non-interacting Bose gas, where AI dagger is a creation operator and AI is annihilation operator. Now, the operator AI dagger and AI, what it does, it counts the number of particles in the ith quantum state. So this Hamiltonian sums up the energies of all the particles. It sums up energies of all particles across all the states that are available. Now, so this is how the Hamiltonian of a non-interacting Bose gas can be written down. Now, using this formalism, we can derive what is the famous distribution, what's known as Bose-Einstein distribution. So this leads to derivation of Bose-Einstein distribution, which gives us the average number of bosons in a quantum state at some thermal equilibrium. Now, this is crucial for describing the phenomenon like Bose-Einstein condensation. Bose-Einstein condensation. Now, as we know, using quantum statistics, we can calculate this probability. I mean, at thermal equilibrium, we know it from quantum statistics that at thermal equilibrium, the probability of a given occupation number in the state, which I have defined as phi I, is governed by a distribution. And what's that distribution? Ni is 1 by e to the power of ei minus mu times divided by kbt minus 1. This is our Bose-Einstein. This is our what we call this as the probability of a given occupation number in this state of phi I, and it is governed by this equation, and this equation can be derived using quantum statistics. Now, this EI is the energy of the state. This is the energy of the state. And mu, this mu is called chemical potential. You have done it in the course of statistical mechanics. And this mu adjusts to conserve the total number of particles. This mu adjusts to conserve total number of particles. And Kb is the Boltzmann constant, and T that we have here is the temperature. Now, this formula shows us that at low temperatures, many bosons can occupy the same state, leading to the macroscopic quantum phenomenon like Bose-Einstein condensation. Sorry. Now, what is this Bose-Einstein condensation? I think there is a need to have a small description of this Bose-Einstein condensation. I mean, at temperatures close to absolute zero, a large fraction of bosons can occupy the ground state. I mean, the lowest energy state. A large number of these bosons can occupy. This phenomenon is called as Bose-Einstein condensation, and it occurs when the thermal de Broglie wavelength of the particle becomes comparable to the interparticle distance, a very close approximation. So this condensation occurs when de Broglie wavelength of the particle becomes comparable to the separation between the two particles. Now, below a critical temperature Tc, now a macroscopic number of bosons are occupying the ground state, and what they form the Bose-Einstein condensate. Bose-Einstein condensate. Now, in second quantization, the state of the Bose-Einstein condensate can be described by the macroscopic occupation of a single quantum state. I mean, the creation and annihilation operators for this state behave differently because the occupation number becomes so large that quantum fluctuations are relatively insignificant. So, for interacting bosons, the Hamiltonian includes the terms. So we are assuming a non-interacting Hamiltonian for the bosons. Now, if we have the interacting bosons, the Hamiltonian includes terms representing the interaction between the particles. The typical interacting, I would call it interacting Hamiltonian. It looks like this. So we have Hamiltonian, that is sigma I epsilon I, then AI dagger, then I have AI, they are the operators, creation and annihilation operators, then plus 1/2 sigma, then I have I, J, K, and L, and I have VI, JKL, then I have AI dagger, then I have AJ dagger, then I have AK, okay, cap, 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 and I have AL cap. Now, here, this crazy thing, what it does, this VIJKL, what it represents the interaction potential. Interaction potential between the particles. So you have the particles. If there is any kind of interaction between the particles, then you have an interacting Hamiltonian. Now, in the context of Bose-Einstein condensation, the interaction between the particles leads to the correction to the properties of the condensate that we have. That's described by what we call Gross-Pitwowski equation. What's that called? That's called Gross-Pitwowski equation. In what we call as mean field theory. I should write approximation because this is also an approximation. So to conclude this talk, I would rather like to rehabilitate ourselves with a summary in introducing you with the second quantization. This second quantization, what it does basically, it allows us to describe the system of bosons more easily by simply quantizing the states and using creation and annihilation operators. And Bose-Einstein statistics, it allows the multiple particles to occupy the same state, leading to Einstein's distribution and phenomenon like Bose-Einstein condensation. And this formalism that we have, it naturally leads to the macroscopic quantum phenomenon. It leads to macroscopic quantum phenomena, and is useful for describing these interacting systems and many body effects between them.